IP addressing. One of my favorite shows on TV is that crime drama called Numbers. It's the one about the guy who's the FBI agent. That guy used to be in Northern Exposure. And he's got a younger brother who's a math genius, a math whiz. Well, they use math and probability and statistics to crack these tough FBI cases. It's got some real geek stuff and I love it. I think one of his favorite mottos is something like, math never lies, people do. Well, I have my own ideas about computers. It's all zeros and ones, baby. And when it gets right down to brass tacks, networking is really yes or no, on or off, true or false, one or zero. So we're going to be looking at IP addressing in this nugget. We're going to start at the very bottom with the bits. Show my motto. In this nugget on IP addressing, we're going to tackle 6 main knowledge areas. First of all, we're going to look at the overall structure and the binary structure to the decimal structure of the IP version 4 address that's widely in use now. Then, we'll talk about the different address classes that were created to preserve IP address space. Then, we'll talk about private reserved addresses, why they exist and how they're used. We'll look at the concept of IP subnetting. Then, the 3 main ways to assign IP addresses, and then finally we'll finish off looking at IP version 6 or IP next generation. One of my favorite questions to ask in a classroom training situation, which is really kind of a trick question, is how many numbers in an IP address? The IP address that's used, the logical address that moves packets across the internet. And I'll hear different various answers. I'll hear 4. I'll hear 32, I'll hear 16, various numbers. But the truth is, it's really just one number. It's one string of 32 zeros and ones. Remember my motto, it's all zeros and ones, baby. So really an IP address is really a field in the IP header that's appended to the data that's moved between the routers in an internetwork. So here's an IP version header, which is really a bunch of fields that just simply have zeros and ones in them to basically have control information for moving these packets from router to router to router across an internetwork. And you can see down here that you've got 2 fields. These are fields that will actually fit 32 bits. The source address and the destination address, which just happens to be this string of 32 zeros and ones. If I just take those bits and kind of pop them in here, you can see those 32 bits go right there in the source address, and I can pop 32 more down here. That's how it looks to the computer, this string of zeros and ones. Well, what we want to do is, we don't really do well with zeros and ones. As human beings, we would really like to work with, digits. Because why? Because, well, we've got 10 fingers and we use a base 10 numbering system that really kind of fits our physiology and really our mindset. So we want to find a way to convert this string of 32 zeros and ones into some kind of readable format that we can use on applications and configuring our network devices so that packets can be sent to logical addresses across internetworks. Well, let's do that. Now, the first step in creating a readable IP address is to separate these 32 bits, this string of zeros and ones, into what we call octets. So we use a dotted decimal here, this little red dot, to create 1, 2, 3, 4 octets. Now, an octet is basically just a group of 8. I mean, think of like Earth, Wind, and Fire from the 70s, or, some rapper with his posse. 8 people up on stage on Saturday Night Live. So we've got a group of 8 here. Now, to be able to understand how we get this IP address in these 4 octets to a readable decimal format, it really helps to understand the values of the placement of these bits in an octet. So let's talk about that next. I've said this to many of my students in the past, and I'll say it again to you. If you absolutely hate math, you may be in the wrong business because you just can't avoid it. Again, it kind of goes back to the fact that I love that show Numbers because I do really like math. I'm not a math genius or a math whiz, but I do like numbers. And you need to understand here that this octet is really 8 bits. And each one of these bits has a value. The bit on the far right, again, let's just go ahead and imagine that we're taking this first group here, this first octet, and shifting it down here. We've got 1, 2, 3, 4, 5, 6, 7, 8 bits. This is called the low order bit on the far right. Over here on the far left is called the high order bit. Each one of these bits has a value if you turn it on. So if you turn on this first low order bit, the value of that bit is 1. If you go to the second bit, if it's 0, well, the value is 0. If you turn it on, it has a value of 2. The third bit, a value of 4. And you can see how this exponentially doubles as we go. Now, if you take this octet and you add up all of these numbers, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you get 255. Okay? If you don't trust me, grab your calculator and add it up. It adds up to 255. So if you turn all the bits on in an octet, the highest number you're going to have is 255. And we'll see later that that's actually kind of significant. Now, realize that your possible values, the possible number of values is actually 256. Why? Well, don't forget, if these are all turned to 0, okay, remember 0 is a number, so that's a possibility. So between 0 and 255 are your possibilities. That gives you 256. Exponentially speaking, that happens to be 2 to the 8th power. 2 to the 1, 2, 3, 4, 5, 6, 7, 8th power. All right? Are you starting to see the math here? This is really basic high school math. But, and again, let me repeat, if this makes you nauseous just sitting here listening to this, then you might want to reconsider. No, I'm just kidding. You can actually get past the math very easily and have a great career. I'm just trying to give you a hard time. But now, we see that we have a value, we have an octet here. And again, each one of these octets has a maximum value of 255. If you turn all the bits on, you get 255. That's very important. Now, let's take it one step further as we move towards a viable IP address. If we look at the actual first octet, the low order bit is turned off because it has a value of 0. The second bit of the 2 bits turned off. The 4 bits turned off. 8, 16, 32, these bits are all turned off. But the 64 bit is turned on and the 128 bit is turned on. So the value of this octet is 128 plus 64 plus 0 plus 0 plus 0 plus, you get the point here. Basically 128 plus 64 equals 192. That's the decimal value of this first octet. The second group of 8 of that original 32 bits, or our second octet, has a value of turning on the 128 bit, turning off the 64 bit, turning on the 32 bit, turning off the 16 bit, turning on the 8 bit, and turning the remaining 3 bits off. If you add 128 plus 32 plus 8, you get 168. So the value of the second octet is 168. You seeing it? I know you are. Good job. Okay, for this third one, you're on your own. I'm going to let you figure this one out for yourself. Now you can go ahead and pause the video. Maybe you can back up a little bit and go look at the screen that had the original values on this, and then add up these bits and tell me what the value of this third octet is. 101. Brilliant. Excellent job. Again, 64 plus 32 is 96. Plus 4 is 100. Plus 1 is 101. Go ahead, pause the video and figure it out. You guessed it, 45. Okay? 32 plus 8 plus 4 plus 1 is 45. Now we have 4 octets. 192 is the first octet, 168 is the second, 101 is the third, and 45 is the fourth. So now we can see our original string of 32 bits here gets separated by 3 decimal points or 3 dots to create 1, 2, 3, 4 octets of binary numbers that get converted to decimal numbers. 192.168.101.45. Now that's an IP address that I can understand, and my applications can understand it as well. But again, this is an address, right? So just like sending, let's say, a letter through the U.S. Postal Service, I'm going to put some information on the outside of that envelope. Well, that information is going to basically, let's say I'm going to send a Mother's Day card to my mom. On the outside of the envelope, forget the logical name. Forget her name for a second and just realize her address is really going to be kind of a combination of two different things. The locality, her location, and then her house number or her apartment number within that location or region. The same thing here with networking. This particular address is in a particular locale or region. It's on a particular network. And then it's an actual host or an apartment or home on that network. So the IP address here is really two parts. It's the network and then the actual node or host on that network. The laptop, the workstation, the PC, the server, the printer, whatever. Now, here's the tricky part. How do I differentiate between what part of this is the network and what part of it is the host? And nowadays, with this particular 32-bit address, realistically, any one of these octets, this could be the network, or both of these could be the network, or all three could be the network nowadays. We need some kind of mechanism in place for the computer to know what's the network, what's the host. It also helps the network engineer to know that information as well. Let's talk about that next. It's really important now to look back a little bit of history. Remember that the people that were responsible for putting the internet together and coming up with this scheme of logical internet protocol addressing of a 32-bit number. You know, the internet was being used for research and for government uses and basically research facilities, colleges, universities. They really didn't even imagine the World Wide Web at that point, or they figured by that time some new addressing scheme would come about, but it really never happened. And of course, we're dealing with 32 zeros and ones, so obviously there's a finite amount of addresses that can be available. So what they did was to kind of help this process along is they broke up this string of 32 bits into what are called address classes. And within that IP address space of those 4 octets, you've got 5 classes. Class A, Class B, Class C, Class D, and Class E. And everything really kind of falls upon that first octet range. If we go back and look at our IP address, it's that first octet that helps determine which class these IP addresses are in. Now realize that in the beginning, these Class A addresses were all given out to the big kind of backbone companies of the internet. And then along came other companies like Microsoft, and they started grabbing up the Class B addresses. So there really aren't a whole lot of addresses left. As a matter of fact, if you go to a service provider, an ISP, you're probably going to get what's called a Class C address. And then you've got Class D and Class E. Class D is used for multicasting. Again, multicasting is really beneficial to sending information out to a group of people on the internet and addressing them as a group. For example, if you want to do video streaming or you want to do web-based training, things like that. And then E is for experimental. We're really concerned with these first 3 ranges, A, B, and C here. And it really gets down to the number in that first octet. So if the first octet starts with a 1, is a decimal between 1 and 127, then it's a Class A address. As a matter of fact, it's going to be between 1 and 126. Technically, this says 127, but notice here it says the number of networks is 126. Why is one of them left out? Well, because the 127 network is actually used for as we'll see later on, kind of a troubleshooting address. 127.0.0.1 is used as a loopback address. It's used for testing your local system. Now, how many octets are set apart to represent the network? Well, 1. Let's take a look at what I'm talking about here. Here's a Class A address. Why? Because the value of the first octet falls between 1 and 127. It's 12. So, according to the specification, the first octet is the network, and the remaining 3 octets, or 24 bits, represents the host. So as you can see here, with a Class A address, I've only got a handful, 126 potential networks. But within each one of those networks, I can have a whole heck of a lot of hosts. 24, 2 to the 24 power host. That's a lot. Now let's go back and look at that diagram real quick. It shows you here, since you're only using the first octet to represent a Class A network, that gives you the potential of 126. Again, we can't use 127, and it gives you per network. So for each one of these 126, let's say it's 126 different companies, different large corporations, each one of these corporations can have 16,777,214 hosts or nodes per network. That's a lot. Now, all of your modern operating systems and most of your applications can look at the value of this first octet. It can look at the bits, realize where the decimal falls, and it can know if it's a Class A, Class B, Class C, or Class D address. But another mechanism that we use mathematically to differentiate and to set apart this particular network is what's called a subnet mask. What we have here is a subnet mask, and this is a set of zeros and ones that kind of tells us which part of the address is the network portion and which part of the address is the host portion. And again, this is a Boolean algebraic process. We're not going to get bogged down in that. Just realize this. In your subnet mask, every bit that gets turned on represents the network. If the bits are turned off, that represents the host. So as you can see here, all 8 bits of the first octet of the 32-bit subnet mask are turned on. That basically tells the application that, you know what, all 8 bits of this first octet represent the network. Okay? This octet is all host, this octet is all host, this octet is all host. So the default subnet mask for a Class A address is going to be 255, first 8 bits, all network, .0.0.0. Another common address class that a lot of companies that are very familiar to you out there have is the Class B address. If the decimal value of the first octet is between 128 and 191, then it's going to be a Class B address. It takes the first 2 octets in the IP address to represent a Class B address. The possible number of networks in a Class B address is 16,384. So there's over 16,000 possible Class B addresses out there. For each one of those Class B networks, each one of these 16,384, each one can have a possible 65,534 hosts. As a matter of fact, this amount of hosts here represents the number of bits that are left over for the network, which is a 16-bit number. Now, this isn't all the possibilities because you can't use the 0 and you can't use the highest possible number for the network. We'll talk about that a little bit later on because each network has to have a broadcast address, an address that represents all the hosts on that network. So mathematically, this won't equal all the possibilities. But you really want to memorize from this table. One of the most important things to memorize from this table is what is the first octet range of a Class A, Class B, and Class C. Okay? Class C falls between 192 and 223 in the first octet, and it takes 3 octets to represent the network. So if you're using 3 octets or 24 bits to represent a Class C network, that gives you a whole heck of a lot of networks. That's why the chances are, if you go to an ISP or a vendor, you're going to get a Class C, because why there's so many of them? Over 2 million of them. But But for each one of these Class C networks, you've only got 254 hosts per network. Now think about it. If we're using the first 3 octets for a Class C, let me change my pointer here. If we're using the first 3 octets represent the Class C network, and I'm going to talk about this because it's so common, that only leaves us 1 octet or 8 bits for our host per network. Let's jump to a Class C example real quick. Here's a Class C address. How do we know that? Well, because of the value of the first octet. It's between 192 and 223. We also know from the table that a Class C address, the first 3 octets represent the network, which gives us over 2 million possible networks, but then the last octet is used for the host. And you can see here in our subnet mask that it represents that exactly. According to the mask, all 8 bits in the first octet, all 8 bits in the second octet, all 8 bits in the third octet are turned on in the 32-bit mask. That means that's our network. Then the last 8 bits represent the host. Now in the table it said that your hosts, all your possible hosts was 254. But we know with 8 bits that the possibilities are 256. Well, what happened to the other ones? You got 2 that are missing there. Well, here's what happened to them. 192.168.101.0 is the actual network number. Okay? If it's a letter to my mom, think of it as the actual city, state, zip code that she's in, the region. And also 255, or if you turn all these bits on, 255 is what's called the broadcast. In other words, if I want to send a packet to everybody, to every host, every node on the 192.168.101.0 network, then I would simply use the address 192.168.101.255. That's the broadcast address. Every network has a network address, .0, and a broadcast address, .255. Therefore, since I can't use the network and I can't use the broadcast, that only gives me 254 possibilities. That's why for every Class C address, you've only got 254 hosts. And that's really important because if you go to an ISP and you say, I want a public IP address that can make my workstations and servers and laptops and other stations visible with routable IP addresses to the public internet, if they give you a Class C address like this one, you've only got 254 addresses. So if your company grows beyond 254, you had to go up and buy more Class C addresses. Or you could just use a Class B that we saw earlier that has a lot more hosts per network. Okay? Fewer networks, you don't get 2 million, but you've got 65,534 hosts per network. That's why Class Bs are also very popular, especially on small to medium-sized businesses and larger organizations. So again, our Class A, Class B, Class C addresses, it's very, very important to memorize some key information. For your exam, you want to memorize of Class A, B, and C, what number is the first octet range. And they'll, of course, give you an IP address and ask you what class is it in. It also helps to know memorize how many networks you have per class and approximately how many hosts you have per class. Okay? Good information to know. Also want to know and memorize the default subnet mask for your Class A, Class B, and Class C network. So since Class A uses 1 octet for the network, the mask is going to be 255.0.0.0. Since your Class B uses 2 octets, the first 2 octets for the network, the subnet mask, the default is going to be 255.255.0.0. See the pattern? And then your Class C subnet mask, which uses 3 octets for the network, the mask is going to be 255.255.255.0. Now, it didn't take long to figure out that, you know what, we want to use the TCP/IP protocol for our applications and for our organization, but we don't really want the IP addressing scheme to make our hosts available or to make our particular workstations and servers visible to the outside public internet. We also want to have some IP addressing to use for testing purposes, for training purposes, for internal use only. So some addresses have been set aside, private addresses, reserved addresses, from each one of the ranges, Class A, Class B, and Class C. So you also want to memorize the fact that from 10.0.0.0 all the way to 10.255.255.255 in the Class A range, these are private reserved addresses. In other words, if a packet that has the address of 10.1.0.0 hits a router, let's say that's at the edge of a large organization or in an ISP or a service provider on the internet, that packet's going to get dropped. It will not be routed. It's recognized as a private reserved address. Same thing for Class B. Anything between 170.16.0.0 all the way up to this address is also going to be a private address. And you've also got a range of Class C, 192.168.0.0 up to 192.168.255.255. And you'll see these addresses used whenever you're like looking at training books that are out there. Some of the addresses that are used for examples and training commonly use address ranges from these private reserved addresses. These are based on one of the documents that's used to define internet standards. It's called a request for comment, and the number is 1918, or request for comment 1918. If you just go up and Google RFC 1918, you're going to get a request for comment, and this is basically the address allocation for private internets. These are the documents used to create internet standards and specifications out there. It gives all the information here about the address space that's used for these reserved private addresses. Now, I mentioned that you'll use these addresses for testing and for lab purposes and for training purposes, but lots of companies will use these internal reserved addresses for their normal operations. Let me talk about that for a second. What a lot of companies will do is they'll go ahead and use a private network somewhere in this Class A range or Class B range, and they'll actually assign IP addresses from this private reserved pool to the hosts inside their corporate network. And what happens is they have in place some type of firewall. This is a logical symbol for a firewall. And on that firewall, they're running some software called network address translation. And again, realize that network address translation and private addressing is a mechanism that's really put in place to kind of help extend that IP version 4. Remember, there's only a finite number of addresses in that 32-bit address space, and quickly, when the World Wide Web came into being early on in the 90s, man, just the explosion, and we ran out of addresses really quickly. So network address translation allows different companies, they can use the same IP addressing scheme inside their corporate networks. You could have more than one company using a 10.10 network or a 170.16 network. But what happens is out here on the firewall, they'll have a public IP address that's valid, not from this private range, but one of the valid IP addresses in the Class A, Class B, or Class C range, and that address is used to represent their company and all of these hosts to the public internet out here over this wide area network connection. So private addresses are used for testing, they're used for training, they're used internally for private uses, but they're also used as a kind of an addressing scheme inside corporations to extend the finite number of addresses available to us in the IP version 4 scheme. Again, network address translation and private reserved addresses. Remember earlier we looked at this Class B address and this Class C address, and we realized that this Class B address, since it uses 2 octets or 16 bits to represent the host, that gives me 65,534 hosts per network. Well, think about it. You're not going to find an Ethernet domain or a local area network that has 65,000 hosts in it. So it's very likely you might want to break down this domain of 65,000 possibilities into subdomains, what we call subnetworks. If you're a small business and you've got one Class C address here, we know that we have 254 possibilities. But even my small business might want to break down this 254 IP addresses into departments. I've got my sales department, I've got my finance department, I've got my customer service department. I might want to put each one of these in their own department, their own subdomain, their own administrative network, and we call these subnetworks. Well, to create these subnetworks, we have to kind of play around with these subnet masks a little bit to kind of get smaller networks created from our major networks. Now, let me just say one thing here, a little caveat. One thing that really pleases me about the Network Plus exam is that you don't have to exert all the mental energy to learn and memorize how to logically subnet a network in your head. I think it's really an overrated skill. As a Cisco CCNP, I can subnet with the best of them in my head. But the bottom line is there's plenty of subnet tables out there and subnet calculators that basically you can just kind of pull them up and say, you know what, I have this many networks and I need this many hosts. Type in some numbers, boom, and it gives you the addresses that you can assign. And you can either assign these numbers manually to all of your workstations, or you can use, as we'll look at later or talk about, you can use DHCP to create individual scopes, and then you can just place those address ranges and have DHCP dynamically assign these addresses and subnet masks. You know, bottom line is, give me somebody who can troubleshoot and secure a network any day over somebody who's a Boolean algebra expert. So we're going to talk about why you would subnet and the advantages to creating subnets, but we're not going to get into the mathematics of it because literally I could spend a couple of hours on it. And you don't need to know that for the Network Plus exam. That's great news. Now, realistically, whether your address class is Class A, Class B, or Class C, you may want your entire network to be broken up into subdomains, into subnetworks that are smaller than 16 million or 65,000 or even 254 hosts. You've got different business units, you've got different departments, you've got different projects, you've got different geographical areas. The list goes on of why you want to subdivide your network into smaller units, smaller chunks for administrative purposes, for geographic purposes, for political purposes, for security purposes. Well, let's look at this Class C here real quick. If my small business has a Class C address or a Class C network of 192.168.101.0, I know that by default, with a subnet mask of 255.255.255.0, the first 24 bits are the network, the last 8 bits are the host. That gives me 254 hosts because I can't use 0 for the network and 255 is the broadcast. But I might want to break up this 254 address space into 4 departments, again, for a wide variety of reasons, 4 subnetworks. In this case, all I simply do is I just manipulate the subnet mask. For example, right now, by default, with 254, all 8 of those bits in the subnet mask, if you look down at the bottom here, they're turned off in the last octet of the subnet mask, meaning all 8 bits are for the host. Well, if I want to get and create some subnets, all I do is create a separate partition and say, you know what, I'm going to use the first 2 bits for subnetworks, or I could say, you know what, if I need more networks, I just grab the first 3 bits of the last octet and create some subnetworks out of that. Now, the more bits you use to create subnetworks, again, the fewer hosts you have per subnetwork. So if I want to create 4 subnets where I had one large network originally, I could use a mask of 255.255.255.192, which is the first 2 bits, which is 128 plus 64, say you turn those on, it gives you 192 instead of 0. I can use that subnet mask for all the hosts in my company, and that gives me 4 subnetworks. Now, of course, the more subnetworks you create, remember, for each subnetwork, I've got a network number and I've got a broadcast on that network. So it effectually starts kind of diminishing the amount of available addresses I have. The more subnetworks I create, the more network numbers, the more broadcast numbers, and again, I get fewer overall addresses. So this 254 gets depleted more and more by the more bits that I use to create subnetworks. Now again, as I said, there's plenty of subnetwork tables and subnet calculators that you simply go, okay, I've got a class B number or a class B address, I've got a class C, I've got a class A, here's my IP address, how many networks do I want, how many hosts do I want, and it gives you the address ranges to assign. But IP subnetting is basically used for those reasons. Now from a network design standpoint, the main thing I've done here by using this router and using IP subnetting is I've created now from one large broadcast domain or one large network, I've now created 4 smaller broadcast domains. Now, what do I mean by broadcast domain? Well, think about it. As before, I had this one Class C network, and 101.255 was the broadcast address. So all 254 hosts, let's say I used up all my addresses, if I send out a broadcast packet, over 200 hosts are getting that package. Well, by creating broadcast domains, I'm basically saying that the finance department here, only people in the finance department are getting broadcasts from other people in the finance department. Only people in the sales department are getting broadcast packets from other salespeople. This is a very important concept, not only for keeping down my bandwidth usage and creating a more efficient network, but I might not want my sales group, or let's say my accounting and finance group, sending broadcast packets into my sales group or maybe into my customer service group. I want to create broadcast domains, and I can use other services, other software on my router to add security and other mechanisms to control traffic as it moves from broadcast to broadcast domain, or subnet 1 to subnet 2. And again, I use routers and IP subnetting as a basic way to do this. Now, something else that was added to the mix a few years ago to kind of help with this process of running out of IP addresses was they said, you know what? Let's just do away with this Class A, Class B, Class C thing altogether, and let's just use what's called classless interdomain routing, CIDR or CIDR, or I've heard it pronounced CEDAR as well. What CIDR basically does is this. You take your IP address. Let's go back over to that other screen. What classless interdomain routing basically does is says, you know what, now we have the entire 32-bit IP address space. There's no more Class A, there's no more Class B, there's no more Class C. You just take your IP address, and then at the end of it, you just put a /, and you say, you know what, how many bits are for the network? Well, for a default Class C, it would be 24. Okay, but in the example I gave you earlier, we saw the 4 subdomains created. We could take the same IP address and just say 192.168.101.45, and since we're going to basically use 2 of these bits here, we'll just say, okay, 24, 25, 26. The first 26 bits represents the network. That gives us what? 6 bits left over for hosts. Well, obviously, if we only have 6 bits left over for hosts, then we're going to have fewer hosts per network. As a matter of fact, it's 2 to the 6th power minus 2, right? Remember that from earlier? Now, why is it 2? Because for each network that we have to take away 2, because we can't use the network address and we can't use the broadcast address on that network. So what CIDR basically does is it gets rid of the classes, and you basically just add or append to the end of your IP address how many bits you're using for the network, and you can do this on any IP address. You could say, you know what, I want to have 172.16.10.50, and I want to use 18 bits for the network. Okay, if I'm using 18 bits from the network, 32 minus 18 leaves what? 14. That gives me 14 bits for the host. So I've got 2 to the 14th power minus 2 hosts. Now again, all of your subnet calculators are going to operate with CIDR or CIDR, so you can go ahead and you can map out your network using CIDR, classless routing, interdomain routing, classless IP addressing, and you can just use your calculator. You can assign your addresses accordingly. Now I'm talking about assigning addresses here. Let's move beyond the math. Let's move beyond the IP addressing, and let's talk about, there's really 3 ways in our modern networks. Let's say we're in a Microsoft environment. There's really 3 ways that we're going to dole out these IP addresses and subnet masks to our workstations, our servers, our PCs, our laptops. There's really 3 main ways. We're going to finish up this nugget on IP addressing briefly talking about those 3 methods. You need to be aware of the fact that there's really 3 main methods for assigning IP addresses to the host on your network. First of all is the static method or manual method, where you actually go to the host itself, log on either through a command line interface or some kind of web access, get access to the graphical user interface, and just assign the IP address and the subnet mask, and sometimes what's called a default gateway, which is the next hop router that you're connected to, and statically assign that. You can also do it dynamically, and the main way that we dynamically assign this is by using a service application called DHCP, Dynamic Host Configuration Protocol, where you create a scope of IP addresses, and basically you assign IP addresses from that scope to particular hosts, and the service does it for you automatically. The client station contacts the DHCP server, and it gets the IP address, subnet mask, gateway information, and a lot of other information as well. Or we can use what's called API-PA, which is the Microsoft term for RFC 3330. This is automatic private IP addressing, and it's basically kind of a failback solution. If your DHCP server is down or you've not properly statically assigned an IP address, it'll go ahead and give your workstation, server, or laptop a temporary IP address from a range of 169.254.0.1 through 169.254.255.254. And the reason why it goes ahead and assigns a temporary IP address from this range, which by the way is not a publicly usable address, is because some workstations and some laptops and PCs need to have their network stack configured and up and running before you can even get into the operating system and do anything. So it doesn't shut you out of the machine because network services aren't operating, especially in dial-up solutions and things like that. So it gives you the ability to kind of fall back on a IP address that kind of places you in a simple, what we call peer-to-peer network. You don't really have any public connectivity, but it does allow you to get your machine up and running till you can figure out what your DHCP problem was, or you can go in and statically assign a proper IP address to that particular host. If I go to the control panel of my Windows XP machine, I go to the network connections area, I'm going to right click on my network interface card and go to properties, and I scroll down here and I find the Internet Protocol. I can double click on that or choose properties. You can see that right now I'm obtaining an IP address automatically. In other words, a DHCP server has assigned my IP address to my machine. If the DHCP server has a problem or it goes down, then Microsoft's API-PA is going to kick in, and I'll get one of those addresses. Just remember, if I get an API-PA address, I can only talk to other computers that are on that same API-PA network, and the chances are I may be the only one. Or I can use the following address, and this is what we call static assignment, where you type in an IP address, 192.168.101.45. We'll use the example address. I could use the subnet mask, or if I'm in that situation from earlier where I have subnetworks created, I would use the mask 192, and then the default gateway is simply the router that this particular machine is connected to. And if you go back to that diagram that we saw earlier with the 4 networks, it would be the IP address assigned to the interface on that particular router. Typically, this workstation will be connected to a hub or a switch, which then is connected to a router that has a valid IP address on this same network. So that's a static or manual configuration. Before we leave this nugget, I got to tell you that the future is here. IP version 6 is already being put in place to replace IP version 4. IP version 6, also known as IPNG for IP Next Generation. It greatly expands the address space. It enhances the security of your IP addressing, and it improves quality of service over IP version 4. Bottom line, with quality of service, you can just do a whole lot more with that particular IPv6 address. There's a lot more space, a lot more fields to control and manage how that particular address is used and moved. It's governed by the Internet Task Force, IETF. The IP version 6 address space is 128 bits, so it's huge. It's a huge number, 340 undecillion, whatever. It's just a gigantic number, 340 undecillion. IP version 4, the 32-bit address space, is about 4 billion numbers, which sounds like a lot, and it seemed like a lot to the founders of the internet too, but think about it. China, India, South America, well, you do the math. 4 billion, not going to cut it. So we've got IP version 6 with its 128-bit address that's expressed in a hexadecimal format. Here's an example of what an IPv6 address would look like. This is really the basic information for the exam, but if you want to dive deeper into IP version 6 and look at all the ins and outs and nitty-gritty, here's a great website for a tutorial for IP version 6. You can jot this down and go check out this PDF file, this Adobe Acrobat file, and download it and get this little 8-page document that goes into much greater detail about IP version 6. All right, that's IP addressing for your Network Plus exam. A lot of math, a lot of numbers, but you did a great job. You're now a binary person. Zeros and ones, baby. We'll see you in the next nugget. In this nugget, we conquered 6 key knowledge areas. First of all, the overall structure of the IP version 4 address, the different address classes focusing on Class A, Class B, and Class C. Then, the private or reserved address space within those classes, looked at the reasons for using IP subnetting and how it's done. Then we looked at address assignment methods, 3 main methods: static, DHCP or automatic, and API PA, and then finally IP version 6. I hope this CBT nugget's been informative for you. I want to thank you for viewing.